Welcome to section 5.3. Today we want to talk about what it means to diagonalize a matrix, when you can do it, and then an optional topic at the end that you can read about is an application of diagonalization, and that would be how to compute powers of a matrix. So let's start out with a review of finding eigenvalues and eigenvectors. So here's a 2x2 matrix A. I want to find, first of all, the eigenvalues. So I'm going to need A minus lambda I, and so that's the matrix 3 minus lambda, negative 1, 1, 5 minus lambda. To find the eigenvalues, I want to solve the characteristic equation. Determinant A minus lambda I equals 0. So 0 equals determinant sign, and I put in A minus lambda I. All right, that gives me, I'm just going to do this in my head, multiply 3 minus lambda times 5 minus lambda, and that'll give us lambda squared. The middle term will be minus 8 lambda. The last term will be 15, but then I need to subtract a negative 1. So that gives me plus 16. And that factors, so I'm going to write down the characteristic equation. 0 equals lambda minus 4 quantity squared. All right, so lambda equals 4 is the only eigenvalue. And note, the AM, the algebraic multiplicity of 4 is 2, because that's the exponent. So we'll look at that in a minute. Find a basis for the eigenspace corresponding to lambda equals 4. So now I want to solve A minus 4I times x equals 0. Find a basis for the null space of A minus 4I. So I'm going to take A minus 4I, augment with 0, and that's, if I put 4 in for lambda in the matrix above, I get negative 1, 1, 1, 0, 0. Okay, reduce that, bring the 1s to the top, kill off this row. So x2 is t, x1 is negative t, and a basis for the eigenspace is negative 1, 1. So the eigenspace is one-dimensional. The dimension is the number of vectors in a basis. So the eigenspace is one-dimensional. So that tells me the geometric multiplicity of lambda equals 4 is 1. Okay, so again, I'll come back to the meaning of the fact that the GM is 1, yet the AM is 2 in a minute. Here's the definition of diagonalization. If you've got a square matrix A, it's diagonalizable if it's similar to a diagonal matrix. And that means, from the definition of similarity that we looked at last time, this means A can be written as PDP inverse, where D is a diagonal matrix and P is an invertible matrix. So for example, I claim that this A is diagonalizable with this D and this P. And so what we would have to do is check, is A equal to PDP inverse? But it's quicker to multiply both sides of this equation by P and just check if AP is PD. And so I went ahead and did that. I got this matrix here, and yes, they're equal. But I just want you to note, again, when you multiply by a diagonal matrix, it scales the columns of A. So the first column gets scaled by 5, and the second column gets scaled by 4. Okay. So that's always an easy check when D is diagonal. Theorem if A is n by n, A is diagonalizable if and only if A has n linearly independent eigenvectors. So the matrix we started with up here couldn't be diagonalizable because it only has one eigenvalue and a basis for the eigenspace only has one vector in it. And so A is 2 by 2, we would need two linearly independent eigenvectors for A to be diagonalizable. Now, I'm going to just run ahead and show you a quick cheat here. This theorem's true, but let me show you a more comprehensive theorem that we'll look at in a few minutes. An n by n matrix is diagonalizable if and only if it has n linearly independent eigenvectors. Yes, we saw that. But here's an easier one. It's diagonalizable if and only if the GM equals the AM for each eigenvalue. The GM equals the AM. Well, we saw in that example up here at the top of the page, the AM was 2 and the GM was 1. So automatically A is not diagonalizable. Okay, let's look at an example where A is diagonalizable and how to diagonalize it. So here's the steps for diagonalizing. You have to find the eigenvalues. Those are going to go into the matrix D. Then you're going to find n linearly independent eigenvectors if you can. If you can't, you can quit because A is not diagonalizable. But if you can, those are going to go in as the columns of the matrix P. And they have to match the way you put the diagonal entries in. So if you put lambda 1 in as the first entry of D, then the eigenvector corresponding to lambda 1 has to go in as the first column of P. And I'll show you exactly what I mean when we do this example here. And then safety check, is AP equal to PD? Personally, I wouldn't do safety check unless I was taking a test or sending someone to the moon and it was very important consequences. But doing your homework, you can just click on, submit, and the computer will tell you if you did it right. Okay, diagonalize A if it's possible. Yes, it is possible. So first step, we need to find the eigenvalues. So we're going to solve the characteristic equation. So I put in A minus lambda I in here, and then I put the determinant bars, and I set it equal to 0. Now, this is not a diagonal matrix, so we actually need to do some work. I'm going to do cofactor expansion on the top row, because that'll be easy. That's 2 minus lambda times the subdeterminant, 2 minus lambda, 1, 0, 1 minus lambda. So that determinant's 2 minus lambda times 1 minus lambda. So altogether, we're going to have 2 minus lambda quantity squared times 1 minus lambda. And I've got my equal 0 on that side. So my eigenvalues are lambda equals 2 and 1. And the algebraic multiplicity, so lambda AM 2, 1. The algebraic multiplicity of 2 is 2, and the algebraic multiplicity of lambda equals 1 is 1. All right, so for lambda, now I'm going to find bases for the null space of A minus lambda I, so for the eigenspaces. For lambda equals 2, I want to solve A minus 2I times x equals 0. All right, so I'm going to reduce A minus 2I augmented with 0 and find a basis for the null space of A minus 2I. So that gives me A minus lambda I is up here inside these determinant bars. So if you take lambda and replace it with 2, you'll see that you get zeros across the top. And then the second row becomes 1, 0, 1. And then the third row is negative 1, 0. I need to make this bigger. Negative 1, 0, negative 1. Augment with 0, 0, 0. So that will only take one step. We'll move the 1, 0, 1 on top and then kill everything else. So x3 is free, x2 is free, call that S, that's a 2, and x1 is negative x3, so negative t. So a basis for the null space would be, I'll put my, let's see, t vector first. So the t vector would be negative 1, 0, 1. And then the s vector is 0, 1, 0. Okay, I'm going to name this P1, call this P2. All right, for lambda equals 1, I want to solve a minus I times x equals 0. So I want to reduce a minus I augmented with 0. So I get 1, 0, 0. So I'm up again. If you put 1 in for lambda in this matrix inside the determinant bars, you'll see you get 1, 0, 0, and then 1, 1, 1, and then negative 1, 0, 0. And then these guys are all 0. So that's going to be, we can do this all in one step. Just use this top one to kill the guys below, and we'll be good to go. 0, 1, 1, 0, 0, 0, 0, 0. So x3 is free. x2 is negative x3, so negative t, and x1 is 0. So basis would be 0, negative 1, 1. We'll call that P3. So now I'm ready to go. I've got my eigenvalues and my eigenvectors. I'm going to let P be the matrix. I'm going to put in the vectors P1, P2, and P3 in that order. So I'm going to get negative 1, 0, 1. I'm putting them in as columns. 0, 1, 0. And then 0, negative 1, 1. So I put P1, P2, P3. So if I do that for D, I need to make the diagonal entries correspond to these eigenvectors. So P1 and P2 corresponded to lambda equals 2. So I need to put a 2 there and a 2 there. P3 corresponded to lambda equal, I can't even remember, 1. So I put a 1 there. And is that right? My eigenvector? Yeah, okay. So, and then fill in zeros. That wasn't the only choice, though. If I had wanted, let's say, P3 first, I could do that. If I put the P3 first, the 0, where is it? Yeah, 0, negative 1, 1. Then in my diagonal matrix, I would have had to put the 1 first. So I have that option written here. If you put the P3 first, then the 1 needs to come first. If you put the P3 sandwich between P1 and P2, that's fine. You just need to take this 1 and sandwich it between the two 2's. If you'd wanted to keep the order like I have it, with the diagonal matrix going 2, 2, 1, there are actually two options for your columns. You could have picked the option I picked, P1, P2 for the first two columns, or you could have put in P2 and then P1. Just make sure that the diagonal entries match the eigenvector that they correspond to. I hope that's clear. If it's not, then definitely ask me during Zoom session. Okay, so it's PP time. Pause and practice. Pause the video, diagonalize this matrix, and to make your life a little shorter, you don't have to compute the characteristic equation. The eigenvalues are negative 1 and 14. Oh, one thing I want to mention before I have you stop is notice the notice that this matrix was diagonalizable, and it's because it had 3 linearly independent eigenvectors. And another way to check is the AM equal to the GM. The AM of lambda equals 2 was 2, because that was the exponent up here. The GM was also 2 because we found 2 basis vectors. All right. And then the smallest the geometric multiplicity can be is 1, because you're always going to have at least one basis vector. So this is going to be 1, which matches the AM. So in each case, the AM matched the GM, which is that theorem I was referring to at the end. Okay, pause and practice. Okay, you're back. So let's make this go as quick as we can. A minus lambda I, I'm going to put over here, that's the matrix. 4 minus lambda, and then 4 minus lambda, 4 minus lambda. Those go in on the diagonal, and everything else is a 5. So we're given our eigenvalues. So let's start with lambda equal -1. I want to solve a minus 1i. Sorry, a minus -1i is a plus I times x equals 0. So I'm going to reduce a plus I augmented with 0. Make this long enough this time. And that's going to give me all 5s everywhere except the augmented column. Okay, you guys are experts now, so you can reduce that to 1, 1, 1, 0, 0, 0, 0, 0, 0, all zeros. So x3 is t, x2 is s, x1 is -s minus t. And so we can write down a basis. You can go still, I'm kind of skipping the step where I write down x bar equals t times -1, 0, 1 plus s times -1, 1, 0. But you can still write that. But if you can write down the basis without doing that step, I'm okay with that. So basis for our eigenspace is -1, 1, 0, and then -1, 0, 1. I'm going to call this P1 and this P2. The order that you put them in doesn't matter. Okay, so the geometric multiplicity of lambda equals -1 is 2. We know that the geometric multiplicity is always less than or equal to the algebraic. So I know the algebraic is going to be 2 also. But that is what it is. So I know that when I write down my diagonal matrix D, the eigenvalue lambda equal -1 will appear twice. It's going to have to appear once to get paired with this guy and once to get paired with that guy. So lambda equals 14. I want to solve a minus 14i times x equals 0. So I'm going to reduce a minus 14i augmented with 0. And I'm just going to write down this matrix, which when you put in -14 for lambda, you get -10 on the diagonal and 5s everywhere else. 0's over here. And I'll just let you, I'm going to put ... confirm that you can reduce that to 1, 0, -1, 0, -1, no, 0, 1, -1, and then all zeros. It only takes a few steps. So x3 is t, it's free, x2 is t, and x1 is t. So our basis is 1, 1, 1. I'll call that P3. I'm ready to build D and P. The order you build them in doesn't matter. I'll do P first, and I'll put in my columns P1, P2, P3 in that order. -1, 1, 0, -1, 0, 1, and then 1, 1, 1. And for D, since I put in P1 and P2 first, I need the -1s to go here and here. And then P3 corresponds to lambda equal 14, so that goes there, and everything else is zeros. Now, if you labeled your P1 and P2 differently, if you want to keep this same D, then another P that would be correct would be just switching the P1 and the P2. -1, 1, 0, 1, 1, 1. That's fine also. That would match that D. So here's two different P's that match the same D. Okay, we're almost done. Don't worry, no more computations, just some short answer stuff. So here's a simple one. If the matrix A is factored as P, D, P inverse, what are the eigenvalues? And find a basis for each eigenspace. So the eigenvalues are sitting right here on the diagonal of this matrix, because this is D. So lambda equals 6, that's one eigenvalue, and a basis for its corresponding eigenspace would be, since the 6 is first and second, here's the matrix P here, I want columns 1 and 2. -2, 0, 1, 0, 1, 0. And lambda equals 5 is the other eigenvalue, and it has basis, the eigenspace has basis, this third column, -1, 2, 0. Okay, so that theorem I mentioned, we've already talked about A and B, so these are equivalent statements. A has n linearly independent eigenvectors will happen if and only if the geometric multiplicity is equal to the algebraic multiplicity for each eigenvalue. For example, in example on the second page when I did that big diagonalization, and in the one you did for practice. And then this third part, if A has n distinct eigenvalues, then A is diagonalizable. Okay, so if A is 3 by 3 and there are 3 distinct eigenvalues, then A is automatically diagonalizable. You don't have to show anything. There's no converse. So if A is diagonalizable, it doesn't necessarily have to have n distinct eigenvalues. And an example is the one we just did. So this one, this matrix here was diagonalizable, but it only had 2 distinct eigenvalues. Okay, so it's a one-way theorem. All right. So explain why this matrix is diagonalizable. So this matrix is lower triangular, and so the eigenvalues are 2, 6, and 1. They're on the main diagonal. There are 3 distinct eigenvalues, and I have a 3 by 3 matrix. So by part C, A is diagonalizable. That's a very long word to spell. I should just sort of put diag. Okay, so part C, A is diagonalizable because there are 3 distinct eigenvalues. Suppose you want to diagonalize a 4 by 4 matrix, and the characteristic polynomial is this. Now I'm saying polynomial because I don't have it set equal to 0. If it were equal to 0, I'd say characteristic equation. What eigenspace are you going to compute first? So there's 3 eigenspaces, the one for lambda equal 1, the one for lambda equal -5, and the one for lambda equals 2. I'm going to do lambda equals 2 first. Here's why. If the GM is 1, the GM has to be less than or equal to the AM. The AM's 2. So the GM could be 2 or 1. If it's 2, then A is going to be diagonalizable, because you're going to get 1 for this, 1 for this, 2 plus 1 plus 1 is 4. If the GM is 1, you can quit, because the GM would be less than the AM and A would not be diagonalizable. Now, the reason why you want to do that first is if you're going to quit, you want to quit right away. You don't want to first do all the work for this, all the work for this, then get to this guy and realize, oh, A wasn't diagonalizable. Hope that makes sense. Okay, a couple more short answers. Suppose A is 3 by 3 and has 2 eigenvalues. If each eigenspace is one-dimensional, is A diagonalizable? Yes, no, can't tell. No, it's not. If there are 2 eigenvalues and each eigenspace is one-dimensional, that's telling us that there are only 2 linearly independent eigenvectors. And we need 3. Suppose A is 7 by 7 and has 4 eigenvalues. So lambda 1, lambda 2, lambda 3, and lambda 4. One eigenspace is 2-dimensional. You're told that. So this one has 2 dimensions. These are the GMs. Another is 3-dimensional. Is A diagonalizable? Well, you've got 2 here. You've got 3 here. The minimum here is 1. Your GM always has to be at least 1. So minimum here is 1. So let's count. This is 5, 6, 7. Yes, A is diagonalizable. I have 7 linearly independent eigenvectors. The dimension of the eigenspace is the number of the linearly independent eigenvectors. So 2 linearly independent, 3, and then 1 and 1. So yes. Okay, here are some where I've just filled in the answers for you, but I want you to take some time to read them. You can see if you left multiply by a diagonal matrix, it scales the rows of A. And these 2 examples come as a pair. They're illustrating the fact that invertible and diagonalizable are 2 independent conditions. One does not imply the other. So I want you to take some time, make sure you understand the hints, give you a hint in each one, make sure you understand what I did. All right, and we're just going to do some true false and then we'll call it quits. A is diagonalizable if A is PDP inverse for some D and some invertible matrix P. False, missing the word diagonal. Just because you call it D doesn't mean it's diagonal. You have to say diagonal matrix D. I guess it would go here, some diagonal matrix D. If Rn has a basis of eigenvectors of A, then A is diagonalizable. That's true. If Rn is a basis of eigenvectors of A, that means you have n linearly independent eigenvectors, and so A would be diagonalizable. A is diagonalizable if and only if it has n eigenvalues counting multiplicity. N eigenvalues. No, that's always true. So this is false. You want n linearly independent eigenvectors. Okay, if A is diagonalizable, it's invertible. False. This one's false. See 4 and 5 above. Okay. A is diagonalizable if it has n eigenvectors. Again, false. It's got to have n linearly independent eigenvectors. And then the last one seemed to be back to B again. If A is diagonalizable, it has n distinct eigenvalues. Again, that's false. The theorem goes the other way. If it has n distinct eigenvalues, it's diagonalizable. But if it's diagonalizable, it doesn't have to have n distinct eigenvalues. So see the example on page 2. Okay, and that is it.